Welcome to our first section on reaction rates. So today we're going to talk about how we describe how fast or slow a chemical reaction happens. So if you think about different chemical reactions or just different processes or any reaction example really, you realize that some of our reactions occur much faster than others. To give you an example, striking a match is a chemical reaction, and this is clearly something that happens very quickly, right? In the span of a second, you strike the match, and now you have a combustion reaction happening, you have fire being produced. It was near instantaneous. In contrast, we know that carbon beneath Earth's surface undergoes a chemical reaction to become coal or diamond or other forms of carbon, but this happens over millions of years. So both of those are chemical reactions with hugely different time spans. So we need a way to talk about those times. We need a way to talk about how long it takes the reaction to finish reacting. And so we're going to use the term reaction rate. This tells us the speed of a chemical reaction, how long it takes it to complete. And like I said, this can vary from near instantaneous to millions of years slow. So in general, the word rate is a measure of change. It's a measure of how much something changes within a specific amount of time. So a rate you're really familiar with is speed. Think about your car. Its speed is measured in miles per hour. So the measurement of how much your distance changed, how many miles you covered in a specified amount of time, 1 hour. And so when we apply this to chemical reactions, we can do really the same thing, a measurement of how much our reactants change in a given amount of time. So in chemistry, when we talk about the rate of a chemical reaction, we're going to use a change in the amount of reactant or product per unit time. So how much of our reactant was used up every second, or how much of our product was produced in 1 second. Here's sort of a visual way to picture this. So let's say this is a chemical reaction in which the red square reactant is converted into the blue circle product. Now, initially, at our time equals 0, before the reaction takes place, we have all red squares. No reaction has started yet. And then with time, as our time increases, more and more of those red reactants get converted to blue reactants until at this time our reaction is mostly blue. And so if we measured this, if we said each interval here was, 15 minutes, we could measure either how many red squares disappear each time interval, and that would give us the rate of our reaction. It would show us how much the reactant is changing every 15 minutes, or we could measure how many blue circles appear every 15 minutes, and that would tell us the same thing, how fast the reaction is taking place. So the question you might be asking is, why do different reactions have such different rates? And to answer that, we have to bring in what's called collision theory, and this is something you're already a bit familiar with. So we're going to use this model of collision theory to relate the properties of the particles in the reaction to the rate of the chemical reaction. And so this will make sense. According to collision theory, atoms, ions, and molecules can react to form products when they collide if the particles have enough kinetic energy. So there's 2 requirements. This is the first one. basically, as the atoms, ions, and molecules are floating around, they run into each other. And if they run into each other fast enough and hard enough with enough energy, they stick together, and that's a chemical reaction. So if we've got two atoms, two types of elements floating around, in order for them to react, they have to form a bond with each other. And in order for them to form a bond, they have to have enough energy. So that's one of our requirements. We have to have the atoms run into each other with enough energy to stick, to form a new compound. So for example, here we have the collision of oxygen and hydrogen molecules to produce water. So as these molecules over here are floating around, they've got to run into each other. They have to collide with enough energy to react and form products. If they don't have enough energy, they'll just bounce right off of each other, and no new compound will be formed. No chemical reaction will take place. So one of our requirements is that we've got enough kinetic energy in our substances to let them react. And the second requirement, you might start to see by looking at this drawing here, the second requirement is that they have to collide with each other in the right way. That is, in order for hydrogen and oxygen molecules in order for them to react and form H2O, the hydrogen needs to run into the oxygen, right? That's fair enough. If the hydrogen runs into the hydrogen, we're not going to make any H2O. There wasn't any oxygen involved in the collision. So we've got these two important requirements. One, the hydrogen has to touch the oxygen. We have to have them collide in that way so that the atoms that we want to bond together actually run into each other and are able to form a bond. And two, if they're colliding in the right way, they also have to have enough energy to form a bond between them to stick together instead of just bouncing off. If they don't have one of these two things, it's called an ineffective collision. No products are produced. The reactants just bounce apart unchanged. So in this example, we've got those same two hydrogen molecules, that same oxygen molecule, but this time it just so happens that both hydrogens run into this one oxygen. Well, that doesn't produce H2O for us because there's 4 hydrogens over here and this oxygen didn't get any, so it wasn't the right orientation. They might not have had enough energy either. It was an ineffective collision. The reactants just bounce off. They didn't make any product. So that first requirement was enough kinetic energy, and this is called the activation energy. It's the minimum energy required. It's the minimum energy that the colliding particles must have in order for them to react. This is typically shown to be like a barrier or an obstacle. It's the obstacle that the reactants have to overcome before the products can form. At the very peak of that barrier, at the top of the activation energy, the particles might form what's called an activated complex. And this is just a fancy vocab word to say they've started reacting. They've started bonding together and forming new things. They're not quite to the finished products yet, but they have started a reaction that will get them to the final products. The activated complex is a really unstable arrangement of atoms. It exists just for a split second when we overcome the barrier of activation energy, and then it allows those atoms there at that peak energy to rearrange themselves and to bond with each other to form the products. And I'll show you sort of a picture diagram here in a second. But this activated complex can form only if we have enough energy to overcome the activation energy, and only if the atoms are oriented properly to have an effective collision. That is, like we saw in the picture, they have to be running into each other in the right way so that the atoms that need to bond together come into contact. Like I said, the activated complex is very unstable. It's really just a stepping stone to the products we want. Its lifetime is very, very short, much less than 1 second. But then it allows us to form the final products. So sometimes this is called the transition state instead of the activated complex. You'll normally hear activated complex, but transition state is sort of an older term that's still in use some places, but they're the same thing. So this diagram here demonstrates these ideas. So here we've got energy plotted on our y-axis and the progress of the reaction on the x. Now we know that the reactants start with some amount of internal energy. We had that last unit, their internal energy. And the products we form are also going to have some amount of internal energy. In this case, we've got the products have a lower energy than the reactants. So we know that energy was released in this reaction. We went from high energy to low energy. So we've got an exothermic reaction here. This also shows us, and this difference in energy levels between the starting reactants and the final products would be our total energy released. That would be our delta H from last unit. But this peak here, this difference between the energy of the reactants and the total energy that they reach in the course of their reaction, this is the activation energy. This is the barrier. The reactants aren't able to just go from here straight down to here. There's a small amount of energy that must be overcome before they can start this favorable release of energy. And there are a couple factors behind this. Essentially, as you could envision, before these hydrogens and oxygens can bond to form H2O, they have to break some bonds up within them, right? Before we can have one oxygen bonded to 2 hydrogens, we need to break apart the O2 and the H2 molecules. So that takes some initial energy in the beginning. So we've got this peak here, this barrier. It has to be reached, it has to be crossed before we can start the downhill slope into making our products. And here at the very peak, for a split second, sometimes we get an activated complex. In this picture, we've got an O2, an oxygen molecule, bonded to 2 hydrogen molecules, one on each side. And this is not a stable molecule. This isn't something that really ever exists. It's just sort of the stepping stone, the in-between phase that forms as these molecules collide, and then they immediately break apart with each oxygen getting 2 hydrogens to make its water molecule. Now, we don't necessarily have to have an exothermic reaction. An endothermic reaction can have an activation energy as well. In an endothermic reaction, we'd have the energy of the reactants. And whatever the energy of the products is, it's slightly bigger, or some amount bigger, than the reactant energy, right? Ignoring the middle part here for a second, our reactants started here at this energy, they ended at a higher energy, so the reaction must have pulled in energy, it must have absorbed energy, and so we've got exothermic. The difference here between the product and reactant energy is the energy absorbed by our system. The difference here between where the reactant started and where they had to get before they could react is, again, our activation energy. So we had to build up, we had to input quite a bit of energy to overcome this barrier, and only then could we start the reaction. So this collision theory is useful for us. It explains why some reactions occur so slowly at room temperature. So for example, we know that carbon and oxygen react when we burn charcoal, hydrocarbons, fuels. We know that this is really common, right? The carbon and the oxygen burn and they make carbon dioxide. But this reaction has a high activation energy. In order for them to react, we have to break bonds between oxygen and bonds between carbon. So we know that there's carbon and oxygen available to us at room temperature as well. We know that if we set out charcoal just at room temperature or outside, it doesn't just spontaneously combust. But our question is why? If it would burn at high temperatures, why doesn't it burn when we just set it on a table outside? Or why doesn't the carbon in our plants, in our pencils, in our bodies, why doesn't that just start reacting with the oxygen in the air? And the answer for that is at room temperature, the oxygen and the carbon molecules are still colliding, but at room temperature they don't have enough kinetic energy to break these internal bonds. They're not able to overcome that activation energy barrier. So the reaction rate is essentially zero. They're not able to overcome the energy barrier to their reaction, and so they are not able to really react at room temperature. In order for them to react, we have to raise the temperature, because in doing so, we will cause the molecules to move faster, they will have a higher kinetic energy, and they will then be able to break these bonds, overcome the activation energy, form the activated complex, and actually react in that case. So there are a couple things we have to consider when we're determining whether or not a collision will result in a reaction. See if you can think of these and recall them. The answer is that the molecules must collide with enough energy in order to react. That minimum amount of energy is defined as our activation energy. They also have to collide at the right orientation for a reaction. So what can we do to affect these reaction rates? Is there anything that we can do to speed up a reaction? See if you can think of anything. If you had a given chemical reaction, you knew its rate, and you wanted to make it go faster. See what things you can think of that might speed it up. There are 4 factors that we can change to influence the reaction rate. So those 4 factors are the temperature, the concentration of our reactants, the particle size, and the use of a catalyst. And we're going to talk about each of these in detail. Let's start with temperature. So as we briefly mentioned, if we increase the temperature, typically our molecules are going to speed up. That means they'll have more kinetic energy. The reverse is true. If we decrease the temperature, molecules slow down, they have less kinetic energy. More kinetic energy will speed up a reaction because more collisions are going to be effective. More collisions are going to have enough energy to overcome the activation energy and have a product. So at these higher temperatures, we've got particles moving faster and with more kinetic energy. So it's sort of a twofold increase here. One, since the particles are moving faster, we have more collisions. Particles are moving faster, and so they run into each other more often. Additionally, a greater percentage of the particles will have enough kinetic energy to overcome their activation energy barrier and react. So increasing temperature increases reaction rate. Our products will form faster. Under a similar thought process, increasing concentration will also increase the rate at which our reactions occur. If you think about having just 2 or 4 particles in a room and they're moving around the room freely, they'll collide eventually. They've got a lot of space though, so it might take them a while to finally run into each other. Now, if we put 400 particles in that same space, statistically we're going to have way more collisions. They're still moving around randomly, but there's a whole lot more of them in the same space, so it's more likely that they collide with one another. So when we increase concentration, we're increasing the total number of collisions that will occur. And so it just becomes more likely that those collisions are effective. If we have more collisions happening, we've got a greater chance that they collide in the right orientation and with the right amount of energy to form a product. Here's an example. We could light a match or a splint just in open air, and it would burn for a small amount of time, but it would eventually go out before the whole splint or whole match burned, because air is only about 20% oxygen, and as you know, fire requires oxygen. The combustion reaction requires oxygen. And so there's oxygen molecules around it, yes, and they're colliding and they're reacting, but that's a slower reaction than it could be because we just don't have a huge concentration of oxygen in our air. Now, by contrast, we could take that same match or splint and put it in a container of pure oxygen, and we would see that it would immediately burst into flame. It would react much more quickly because we've increased the concentration of oxygen molecules available. There's a greater concentration, and so there's a faster reaction in that second case. The third factor was particle size. Now, particle size is different from the others. When it comes to particle size, decreasing the size is going to be what speeds up our reaction, because what we care about when we think about our reaction rate is the total surface area of our reactant available. Because again, we're trying to increase the number of collisions. If we could get more collisions to occur, it's more likely that we'll have more effective collisions. And so if we increase the surface area, there are now more particles on the surface, more particles exposed and available for collisions. And so that will result in more effective collisions and a faster reaction rate. Now, decreasing the particle size is what increases the surface area for us. If you think about crushed ice versus an ice cube, you could have the same total amount of ice. The crushed ice, as you might know, melts faster because it's got a lot more surface area available to the surrounding water. The same is true for our particles. Making them smaller will increase their surface area, increase the particles that are exposed and available for collisions, and so by increasing the frequency of collisions, we can increase the reaction rate. Here's a picture to demonstrate this. These illustrations show magnesium being dropped into water, or I guess an acid-water mixture here. But when this happens, the magnesium is going to collide with hydrogen ions from the acid to make magnesium ions and hydrogen ions. So we've got two situations here. In the first, we've got a solid piece of magnesium, a large chunk that's dropped in. And this reaction is going to happen when these little hydrogen ions collide with the big magnesium ions. Now, when we have a big block like this, these collisions can only happen at the surface. There's a couple depicted here. These ions are not able to get to any of the interior magnesium atoms because they're surrounded by other magnesiums. Only the surface can react. Now, if we instead divided that solid magnesium chunk into a bunch of smaller pieces, we'd have a lot more possible sites for collisions. There are now way more magnesium atoms exposed to the solution and out in the open, and so we have more collisions, a greater chance of having an effective collision, and so a faster reaction rate. The other way we could increase the surface area of a particle is to dissolve it in water. In a solution, the particles are completely separated and so totally accessible to other reactants. This is a really powerful way to speed up a reaction rate. If all the particles are dissolved, then there are no interior particles. There's no particles being hidden or blocked. They're all dissolved, they're all floating around, they're all available for collisions to occur. You could also just decrease the size of the particle itself. So if you had a solid, rather than dropping your whole solid block into your reactant, you could first break it into pieces or grind it into a powder. And the smaller your particle is, the greater your surface area and the faster your reaction rate can occur. This is why really small particles, when you get dust-like size, these are really dangerous when they're suspended in air because the surface area is so large, they've got such an ability to react, they can sometimes be very, very combustible. And so if you get too small, you have to handle them very carefully or they become dangerous. So for example, this used to be a sugar refinery. But throughout the processing of refining the sugar, a lot of dust built up on equipment. And what do we know about sugar? It contains carbon, hydrogen, and oxygen. So it can burn in air. And once that dust was so small, there was such a high surface area that sugar dust was able to react with the oxygen in the air very explosively. It was a combustion reaction, and there was so much surface area because of the small dust particle size that the combustion reaction happened so fast it was an explosion. So you have to be very careful when dealing with dust-sized particles. And finally, the last way to speed up a reaction is by adding what's called a catalyst. These are really helpful for us because sometimes it's just not practical to increase the temperature enough to really influence the rate. Sometimes we just would rather not have to pay for the energy to heat our reaction chamber up to 1600 degrees Celsius. That would be very expensive. If we could find a catalyst to do the same job, we'd be much better off. And so a catalyst is a substance that increases the rate of the reaction without actually reacting itself. A catalyst is not used up during the reaction. It doesn't actually participate in the reaction at all. It's really just a bystander. It's there, it makes the reaction easier, it helps, it makes it go faster, but it doesn't react itself. Typically, what a catalyst is really doing is permitting a reaction to proceed along a lower energy path. Remember that activation energy barrier where we formed an activated complex at the top? What a catalyst will do is lower that barrier by allowing an easier activated complex to form. So let's see what that looks like. This first line here, this would be a reaction without a catalyst. See, it's got this fairly high activation energy that we would have had to overcome by inputting energy in the form of heat, most likely, to get up here. But if we add a catalyst, it lets us take this path down here, a much lower activation energy barrier to overcome. We don't have to input nearly as much energy to get this reaction to occur. And so with that lowered activation energy, a greater percentage of the reactants are going to have enough energy available to overcome this barrier and form products. So the reaction happens more quickly at a greater rate because more of the reactants already have enough energy to react. We don't have to wait for them to build up this huge amount of energy to overcome this barrier. They can just sort of go right through. They've already got it. We typically demonstrate the use of a catalyst in a chemical reaction by placing the catalyst on top of our reaction arrow. And the reason for that is that the catalyst, like I said, is not used up. It's not really participating. It's not reacting. In this example of the reaction between hydrogen and oxygen to make water, if we included platinum in our chemical reaction, it'd be here in the reactants and it'd be here in the products. It's there before the reaction, it's there after. It really didn't do anything. So we tend to write it on top of the arrow just to demonstrate that. So this is a reaction that's actually used. This catalyst is a common catalyst used in this process because we know that hydrogen and oxygen will react to form water, but they don't really do so at room temperature, not naturally. But if we add platinum, platinum allows them to do this rapidly at room temperature. This is a common idea is used in your catalytic converter in your car. If you hear the word catalyst in catalytic converter, the same thing's going on. There's platinum or another precious metal that's placed in sort of a honeycomb shape arrangement in this catalytic converter, and as the waste gases pass over it, they contain a lot of things that you don't want in your exhaust. Carbon monoxide, compounds with nitrogen and oxygen, things that would be much more harmful emissions. And we would like to react those with oxygen to make them less harmful. For example, we would rather release carbon dioxide, CO2, than carbon monoxide. And so we've got this converter with platinum to act as a catalyst to allow the gases that we don't want to react with oxygen to form less harmful emissions. Again, remember, these catalysts are not consumed during the reaction. We don't need to write them as a reactant or as a product in our equation because they're just there the whole time. They're just acting as a bystander. So we write them above the arrow. These are really helpful to us as humans as well because a lot of our body processes are chemical reactions, and at our existing body temperature, these reactions would take place at very slow rates. Luckily, we have natural catalysts in our bodies to help speed them up. And when we're talking about biological catalysts, we call them enzymes. They're the same thing, we just have a different name for them when they're biological. So these enzymes are catalysts that act in your body or in other biological systems. For example, you have a lot of digestive enzymes that allow you to break down protein or other food molecules in a matter of hours instead of having to wait out the really slow reaction rate that would be natural at our fairly low body temperatures. To demonstrate this visually, what an enzyme does, it's almost like a puzzle piece. You can kind of think of it as a puzzle piece where the substance we're interested in fits perfectly into the enzyme. The enzyme is perfectly tuned or calibrated, if you will, to react or to hold a specific target substance. And once it has brought it in, it allows the reaction that we need to occur. And once the products have formed, they break off from the enzyme, and then the process can repeat itself. Of course, we run into problems if something else sits here in this puzzle piece, and the things that do that are called inhibitors. They are the opposite of a catalyst. They interfere with the catalyst action. If something else came and filled this space, the substances that we wanted to react and wanted to use that space would be blocked. They wouldn't be able to fit in here because there's an inhibitor already sitting there. And so that's what is occurring if you hear people talk about enzyme disruptors or other effects in anatomy or biology. You've got a substance blocking this enzyme, and so your catalyst isn't able to be effective. You have to go back, and now you're back to being stuck with the slow reaction rate. I'd like to avoid that if possible. Some inhibitors, in fact, react with the catalyst itself. This is called poisoning. Instead of just blocking the rate, they actually react with the catalyst. And so adding an inhibitor will reduce the amount of catalyst available for a reaction, and so slow it down. The reactions slow down or sometimes even stop if enough of the catalyst is poisoned. All right, so one question for you to sort of review this information. Which of the following factors here could be increased in order to decrease the reaction rate? So think about that to yourself, and I'll bring up the answer in 1 second. We want to increase one of these in order to decrease or slow down the reaction rate. And the answer is particle size. Increasing catalyst would speed up our reaction. Increasing concentration would speed up our reaction. There would be more particles in the same space, more collisions. Increasing temperature would increase our reaction rate. There would be particles moving faster, so more collisions, and particles moving with more kinetic energy, so more effective collisions. Particle size is the one where increasing it will decrease our reaction rate. If we make the particle size bigger, the surface area gets smaller, there are less particles available to react, and so our rate slows down. So just to tie this all in with our previous information, remember today's main idea: we can control the rate of a chemical reaction by adjusting our temperature, concentration, or particle size, or we could add a catalyst to speed up the reaction by lowering the activation energy.